After thinking about the performance considerations for running on GPU versus CPU, the other thing we have to bear in mind are the memory considerations. And we saw in the previous sections, in fact, that one of the most common errors that people see when they're moving computation between the CPU and the GPU is a mismatch between where the data in a particular function are. Right? So having mismatched data between the CPU and the GPU. One of the second most common errors that people see is a memory error. And the reason for this is that GPUs have significantly less memory available than CPUs. So CPUs these days can have hundreds of gigabytes up to terabytes of memories per processor, whereas GPUs are limited to sort of 16 to 32 gigabytes of memory. And this can be a real problem when you are training a large machine learning model, because when it comes to memory usage, it's not just the size of the training data that's important, but also the size of the model itself. And you have to remember that all of the trainable, the learnable parameters in your model also require space in memory. And even more than that, when you're using learnable parameters where historic gradients are being calculated, those are also going to accumulate in memory. So a lot of the stochastic gradient descent learning rate adaptation methods require the presence of historic gradients. So the memory in your GPU can get filled up very quickly. And of course, that's one of the major reasons why we send data to the GPU in batches. And you'll have seen this in your training loop already, that the data in the data loader is sent in batches. So in this section of the lesson, we're going to ask the questions, why do we need to send our data to the GPU in batches? And if we are going to run into memory problems, how can we monitor our GPU memory usage? So the objectives are to understand the issues around GPU memory limits, and also to give some information on where to learn more about GPU memory management. So in the notebook that people have put together at this point, you'll see that your batch size is set to 32. Now what that means is that in our training loop, we are updating our learnable parameters within our neural network model using the gradients from 32 samples at a time. So we're importing data, 32 samples at a time, calculating the loss function, and then the gradient update from that loss function using backpropagation to update the weights in our network. And 32 is a pretty good number for that. So I particularly like the quote from Yann LeCun, who invented LeNet, who said that friends don't let friends use mini batches larger than 32. And in fact, 32 is generally a pretty good number for your mini batches. Now, a mini batch is the name we give to each one of these batches that goes into the training loop. And that's the size of the data sample that's used for each update in the stochastic gradient descent algorithm. And the reason we don't do it just sample by sample is basically to smooth out our training. So if you use a smaller batch size, you'll tend to see that you have a lot more noise in your loss curve. So it tends to be more stochastic. Whereas if you use a larger batch size, then it tends to be quite smooth. But if your batch size gets too big, then you can miss subtleties in the update of the parameters. Now that's got to be reconciled against the fact that, of course, you want to fill up as much of the GPU processing as you can. As we saw in the previous section, our GPU performance improves when we do more on the GPU. So we want to do as much as we possibly can. So in terms of exploiting the parallelization on the GPU, we want to make the batch size as large as possible. However, we have to hold that against the fact that a larger batch size may affect our training by overfitting in each iteration of the batch. So tuning the batch size is something that you typically do at the beginning of a machine learning application where you're really setting things up, and you'll use your validation set to tune the batch size as a hyperparameter for your training loop. However, when it comes to GPUs, the other consideration we have when it comes to batch size is whether there's enough memory available on the GPU for a particular batch size. And when we think about that, we have to bear in mind not just how much memory the batch size itself requires, but how much memory is available to fit both the model parameters and the training batch into memory. So what that means is that for much larger models, your batch size is probably going to be smaller because there's just not enough space for large batches on the GPU. So in this section, we're going to have a look at demonstrating to ourselves that we can run out of GPU memory if we make our batch size too big. Now, to do this, I'm going to cheat slightly because, as we said in the last section, we're using a really, really small neural network. So it's going to take up almost no memory at all on our GPU. So I'm going to cheat slightly and add another hidden layer to our neural network. And I'm going to give this hidden layer the same dimension as our first hidden layer. So I've just added it in here. Let's call it hidden layer 2. Let's add it into the forward step. So you can see how simple it is to add in another hidden layer. So now our multi-layer perceptron has 2 hidden layers. And the other thing I'm going to do is I'm going to increase the batch size. So I basically want to go as big as I can. So let's see, how many data samples do we have in our training data? So if I print out the size, data set of the training data set, that will tell us how many samples we have. There we go, so about 460,000. So I'm going to put all of our training samples into a single batch. So I'm going to try and pass the whole data set through our slightly larger network all in one go. So to do that, I'm going to update the batch size parameter to give it that very large number. I'm also going to make each of the hidden layers in our network have 2,000, no, that's the wrong one, that's the number of classes, hidden size, go from 5 neurons to 2,000 neurons. So in your network, you may already have the hidden size set to 2,000, just left over from the final exercise in the previous section. Okay, so now I've made all those updates. Let's rerun our training. I'm going to rerun the print statement. Let's read in this network again. And here's our training loop. And if I hit go, let's see what happens. We can see that we've received an error. And our error says that the GPU is out of memory. So you can see that by loading in too much data in a batch, we can exceed the memory of the GPU. And when we exceed the memory of the GPU, it basically crashes our process. So we need to be quite careful to tune that value before we start. Now, for an example problem like the one that we've been using in the tutorial so far, which has a very small network and a very small data set, it's quite difficult to run out of memory on the GPU, especially a GPU like the P100, which has 16 gigabytes of memory. However, if you're using a data set that's comprised of, say, images, for example, then your data can very rapidly become extremely large, and you can run out of memory very easily, especially if you're using a network that's deeper than 2 hidden layers, which the likelihood is that you will be. So let's reset our batch size back down to a more reasonable 32. We'll leave the number of neurons in each hidden layer as 2,000, and we'll stick with our slightly deeper two hidden layer network. And we'll use this to see how we can actually examine the memory usage. So within Pytorch, we can use two functions. Well, so there are many functions within Pytorch to monitor memory usage, but within Pytorch there are two particular functions that tend to get used, which I'm going to show you how you can use. So within a particular epoch, let's just add in a couple of these functions. So I'm going to say that A is the memory allocated. Now, the memory allocated is the memory that's actually occupied by tensors on the GPU. So actually allocated is actually used by actual data. The 0 here refers to the GPU index. So in this case, when we only have one GPU, we could in fact just remove that number. Give that extra equal sign. The other kind of memory we have is cache memory. Now, because memory access on the GPU is quite complicated, software packages tend to reserve memory on the GPU in advance because they expect to use it in future, and that's called cache memory. Now, the way that different software packages decide how much memory to cache depends on the package itself. In Pytorch, it's quite a complicated process, and I have to admit that I can't quite follow exactly how the memory is being cached. But essentially, when tensors are moved off the GPU or deleted from memory, that memory is then added to the cache. Now, the available memory at any given time is the difference between the cache and the allocated memory. So it can be a bit complicated to follow. So just for every epoch of our training loop, now with 32 samples, so we should be fine in terms of memory, I'm just going to print out those two quantities. Now, although I'm showing you how to do this and how to take a look at these things, I have to admit that I don't find them very useful. Perhaps if you were trying to tune a process within your training loop very, very finely, you might find that these things help you. I have to say that I find that tuning the batch size using the validation data is generally more useful. Okay, and here we can see some of the memory usage statistics coming out. So very helpfully, these are in bytes. So you probably want to divide them by 1 times 10 to the 9 to get them in gigabytes to see something more useful. But you can see that it's possible to monitor your memory usage throughout your network. Now, the other thing that might interest you when you're trying to work out how much memory you need as a function of model size, perhaps rather than batch size, is that for a neural network, each of the fully connected layers, so the linear layers in Pytorch terminology, have memory requirements that scale quadratically with the number of data points. So you can basically say that your memory usage will be a linear function of the quadratic number of data points. And if you have the same number of neurons in each of your hidden layers, you can say that your memory usage will basically scale linearly with the number of hidden layers in your network. So this has been quite a quick introduction to GPU memory usage. Hopefully, memory should not be a massive problem for the particular problem that you're addressing on your GPU. However, some key points to remember if you do run into issues is that the batch size should only be set when you're considering your optimization as well as your GPU memory usage. So don't set your batch size purely to use up your GPU or just to fit onto your GPU. Do remember that the size of your batches will affect the convergence of your network. The other thing to remember is that memory limits are not trivial on GPU. They depend on both the allocated and the reserved cache memory on the GPU. And that has to incorporate not only the model and the training data in the batch, but also the historic gradients for the trainable parameters in the model. And so you need to bear that in mind. If you do have memory problems, there are lots of helpful resources available online, some unhelpful resources. And in particular for Pytorch, there are several different functions that might help you in order to identify where your problem is coming from. And you can find the links to those resources at the bottom of this page.